All right. Okay, yeah, good morning. Ong Tui from Red Balloon Security. I am up here so this is work that we did over the last 2 years. Lots and lots of people helped out, especially people from, within Red Balloon Security. And there are two authors to two of the papers that we wrote on this, and the United States loved both of them so much that they couldn't leave the country for different reasons. So I'm up here presenting on work that we all did. A lot of people helped out. And without further ado, all right. So slides. Okay. All right. Here we go. Cryo, mechanical, memory, extraction. All right. So this is a talk on freezing RAM chips with a little robot and then getting it off of a device to read the memory so that we can see what computers are thinking, because we almost never know. It's a mystery. And like I said, right, so this is work, like when I started making the slides, I'm reflecting on all of the last 2 years of us working on it, and the greatest philosopher of all time once said, I can't see him coming down my eyes because I gotta make these slides cry. Yo. Eh? All right, Jay-Z, by the way, yes, said exactly that. All right, so this is a story of failure, many failures. So this is like a failure of 7 months of failure inside a longer period of like 18 months of broader failure. And the way these research problems go, we did end with like a tiny drizzle of epic win right at the very end, but this is definitely 18 months of us working through all sorts of shenanigan problems, and finally getting to this place with the robot that I'm going to talk about. It's literally outside the door, so you definitely should play with it. The physical thing right over there. So what do we do? What do we win? All right. So I guess the first thing that we won is we wrote 2 papers, or the first paper over here is about the robot doing cryomechanical memory extraction, and the second paper was basically what we got out of using this robot on a embedded device, and that device happens to be the Siemens S7 1500 PLC CPU, right? So I definitely recommend you check out the papers. I'm going to go over a lot of the practical engineering things that we saw for this project, but there are a lot of technical details both on the Siemens thing and also the robot in the paper. Okay, so, like whatever, that's a paper. So what do we really win? So, over here, right, like in this burgundy color, so that's the market share of Siemens Industrial Control in North America. And this other bar, I think it's for Europe and, some other, for Europe. Yes, so if you average this together, Siemens PLCs probably run something like 40% of the global industrial control market, and this was the thing that we found on it. Okay, so missing immutable root of trust in the 1500 CPU, and these are the devices that it affects. There's a second page. There's a third page. There's a fourth page. 5 and 6. 7, 8, 9, 10. All right, and this is their mitigation recommendations. And I think at the time that we disclosed the vulnerability, probably in February of this year, this affected every single 1500 CPU module that Siemens made. And these things are in the ground for about 7 to 15 years, right? So which makes this response kind of not the best. So this is their recommendation for workarounds and mitigations, right? And this is, industrial control still can't get away with this kind of response. They just say like physical access, right? Lock your door, and your CPU will be cool. And then in terms of fixing the secure boot vulnerability, they just flat out said like, nope, goodbye. No fix, no mitigation, right? Just lock your PLC up and everything's fine. So I think on a meta level, like this was a really good technical sort of achievement for the researchers that did this work, but I don't think this is a good response for, like the world, right? Because, we depend on these things. a lot of the time. So on a technical level, like what did we really win? The game was we stared at this thing and poked at it with stuff until it cried uncle. And if you look at it, it doesn't look all that complicated, right? And we're really just talking about this baseboard over here. It's about yay big, and why is this so hard, and what's the big deal? So, like I said, the big deal on it is this is the current prime time, PLC CPU module sort of offering by Siemens, and they have like 30% of the ICS market globally. So this makes the 1500 line of CPUs, PLC CPUs, probably, I don't know, like single digit, maybe double digit of PLCs like in the ground running critical infrastructure like today. And yeah, and then looking at the hardware, right? So we wanted to first get introspection into the device to see what it's doing, how it's thinking, how it's feeling, and what we found was this looks simple, but there's some elegance to the hardware obfuscation in the design. So it's basically there are three big rectangles that just says Siemens, right? Goodbye. Like it's a pretty integrated custom package, and then on top of that, they did a whole lot of what I call product finishing. So it's not necessarily hardware security, but they did go through this process of actually just removing all the debug interfaces. There was nothing that we really found that allowed us to even look at the boot log, or no JTAG certainly, right? And there was short of observing like the color of an LED when it turns on or when it crashes, there was basically no way for us to introspect the system, as it's running. And on top of that, they have a encrypted bootloader on flash. So every single thing, starting from the boot code to the OS to the user space code, here was all encrypted. So like we looked at this simple little thing and we said, okay, like what next, right? So it was actually really difficult to get our foot in the door to do any kind of security analysis. And like I said, this isn't necessarily good for security. It was just good for obfuscation, and it wasted a whole lot of our time. And I think well, then we did the rest of this. So looking at this board, right? We can't really see inside. So the typical sort of thought. Okay, I'm just not going to move. All right, the typical thought process here, right, is if you can't just JTAG in, what are you going to do? Well, so we can start doing like a lot of different fault injections, right? We can like power it, EMFI, clock glitching, and all of that. But at the end of the day, though, even if we did do something interesting from a glitching perspective, there's still no debug output. We're still looking at that little LED, right? That's as much information as we were able to see from a crash. The next thing may be like, okay, we can decap the chip and like, I don't know, question mark, do some really ninja stuff with a SAM and a fib, but I'm embarrassed to say I don't have a SAM or a fib. So each of, when we're talking about decapping and physical destructive analysis, each of these boards is actually like $1,500, and that's a lot of money, and it takes weeks for us to get these off of eBay, and all of the custom SOC stuff just kind of screamed like really complicated and expensive to us. So that's a path, but we didn't take that. And then the next thing we can try is like, okay, we can like try really hard to find JTAG and some debugging interface, but we did try this, and this became an infinite loop, right? Because like it didn't work, and we come back and we say, let's try really hard, and we just didn't find it. So, and then we can shout and say mean things to the board, but this was shockingly ineffective scientifically. So, we looked at it and we said, okay, like, we can do all of these things, but this path is very custom and not really repeatable across different types of devices. So, that's a whole lot of effort for this one board, and I wanted to create something that was generic and usable for embedded devices across the board that has this level of, finishing and obfuscation, right? But not encrypted memory. So the idea that we had was, right? So then we said the simplest thing to do must be to build a robot, of course, right? And then read its memory, right? And then read its mind. It's from Face Off, like Face Off. And that was the idea. So When I first started talking to people about this idea, a lot of what I got was, oh yeah, Coppin attacks, right? Like this is super well understood and well documented. There are papers on it, and that is true. And this is, I think, a really good paper that got me started thinking about data remnants on dynamic memory. But really cool idea in the paper, but from a quantitative analysis, like in scientific process kind of perspective, that this is the image, right? So that is a person's hand with a can of CO2, right, upside down, pointing at his helpless ThinkPad from, I don't know, like 12 years ago, right? So it's not exactly, all that scientific, and it also didn't really apply to this, right? So the first thing that we, after reading the paper and thinking about it, and when we sat down to actually do this, it was this, like, right? When you have no DIMM slot, so this thing doesn't have a DIMM slot, right? You can't just like remove the module, all right? So at least we had to solve some mechanical process of getting the memory, cold, off of the device and onto something that can read it. And so that was one thing. And then we sat and thought about it for like one more minute, and then like more and more problems started to come out, right? And we're gonna talk about some of those problems. So the second problem, aside from the fact that these things don't have a slot and you have to physically desolder the thing, get it back on, off, on again, was that this module, the CPU, has 5 memory chips, right? And it's LPDDR1, so that's kind of good because like we don't have to maybe work with like fast timing as much, but it has 5 chips, and also it has 3 chips on the top of the board and 2 chips on the bottom of the board, right? So, that's not exactly easy, and the naive way to go about this maybe is to build like PyMate, like 5-prong of like death, right? And simultaneously pull all the 5 chips off. But if you think about how like hilariously not doable that is on our budget, I mean, we didn't do that. So, and part of the project also, the focus was to do this, but also to build it, on a budget for about $1,000, so we can use this on all of the things going forward. So here's the plan, right? First, we're gonna, we have a scrap CNC little engraver thing in the office, so we're gonna first, Frankenstein something that can actually move the memory chip from one thing to another, right? And then, well, at runtime to read the RAM chip. And the second thing is, okay, so we have to rip the 5 RAM chips and reconstruct memory, so the chips are, like the 5 chips are striped together and used simultaneously with ECC, right? If you think about, there are 5 chips, like 4 is probably 32 bits, and the other one ECC. But we're not going to be able to do it simultaneously because that's really complicated. So the idea is we somehow rip the memory chip at the same point in execution many times to reconstruct all of the bits from the memory, at least 5 times. And we're not talking about a gigahertz processor here, but like how do you pull 5 different chips over and over again reliably at like the same, I don't know, 3 or 4 instructions, right? You probably have like 100 nanosecond timing window, which is kind of ridiculous for like a physical piston or a thing to move up and down that reliably. All right, so if we can do that, then number 3, like somehow magically combine, right, the bits of the memory that we extracted across multiple runs. And then who knows what comes after. And then number 5, hopefully at least read the unencrypted boot code or whatever code is executing in memory, right, through the boot process so we can look at it to see, I don't know, what's actually inside. We actually did it. So here, this talk is going to focus on the pragmatic aspect of how you go about building this thing. Like I said, the robot is literally outside, so if you're interested in doing this, play with it, and I'm going to show you basically how to build this for about $1,000 with COTS hardware that anybody can buy. But there are a whole lot more details in the wood paper that is up there. Okay, so let's talk about, so this took, like I said, 7 months of continuous failing and failing and failing, but we're going to fast forward to the solution that we got actually to work. So basically, what did this involve? We needed to build a sufficiently precise linear actuator, right, on a budget, and then we need to find some kind of a magical like RAM socket that allows us to move the thing like from device to device. And if you think about the traditional sockets, like you can have a clip or a clamshell, but building a robot that does that is a little complicated. So maybe find the right socket thing. And then after that, active closed loop cooling for the RAM. And also the reason why we call this, a cryomechanical memory extraction and not just code boot, it's not just we want to be fancy about it, everybody calls it code boot, but if you actually have closed loop active cooling, right, you can then start to pull the memory chip off, after it boots. So it's not just code boot, right, which means that the name itself is a little misleading. You can pull this memory chip whenever you want, as long as you have active cooling that's sufficient, during runtime. So we built that active cooling loop, and then figure out a way to extract the 5 chips at the same time and the same place in code execution, so that way we can actually get, assuming that we have a deterministic execution, right? If we can pull the chip at the right time, then we can actually have a chance of reassembling all the physical memory and then virtual memory and then the code and the heap and the stack and all of that. And then lastly, we built an FPGA thing to do the actual DDR RAM dumping, right? It speaks to a loosey-goosey version of the DDR state machine. And we did this for LPDDR1 and DDR2 and 3. We did all 3 of those. All right, so we're gonna start to hit all of these in that order. So first, right, how do you make a precise-ish, like a linear actuation thing on a budget? Well, we started with this, right? So I actually there's a special place in my heart for things like this. This controller you can just throw away, right? And the motors are okay-ish, but what you get for this money, like, this is actually like a fairly precise and sturdy little body, so the aluminum extrusion is pretty rigid, and inside it has ball lead screws, which actually allows you to move fairly precisely without losing precision and movement. But you buy this, and then the next thing you do is you junk like all of these parts, right? Because out of the box, it doesn't actually get you precise movement, but we'll get there. So the first thing that I did was thinking about, okay, like if anybody has ever done any kind of, like, I don't know, CNC or 3D printing, and if you get your height wrong, right, you can imagine just breaking your tool or dragging things around, and you say, oh man, I gotta start over, this sucks. So, I mean, I knew that, like, just thinking about how expensive this hardware is and how hard it is to actually, like, take a stepper motor and put the thing down at the right place with the right force with a stepper motor, right? The first thing that we did is we took the Z-axis off, and we went with a pneumatic cylinder actuator, right? So, it's exactly what it sounds like. It's pneumatic, it runs on air, it's a cylinder, this, thing, and it has, and it's fairly cheap, it's like $20, but it basically is this airtight piston, right, that, pressurized air moves the thing up and down. So, in order to make this, to machine an air piston, you're gonna have to have a certain amount, right, first of all, of precision in the machining, otherwise it'll leak air and it won't work. But then also, thinking about this, pneumatic means the pressure is being generated by air pressure, so you're literally sitting, on a air cushion when you push the memory chip down. So it has more of a gentle sort of pressure slope, when we actually do the memory pushing and the pulling. So that totally worked out. And then you hook it up to this little pneumatic solenoid, right? You can get like a thing on a manifold, 4 of them for like $40. So this is great, and it's super duper affordable. All right, and also what we found is, these things are typically meant to run at way higher than 10 psi, but I'll show you what happens when you push like a memory chip with air at like 100 psi, right? It screams and it cries and it dies. So we dialed it in, so anywhere between like 7 to like 15 psi is really the sweet spot. So you need a little pressure regulator, but we're running this thing way lower than standard psi on it, but it was very gentle and it worked. Okay, so then the next thing is, all right, so when you buy this thing, right, it looks great, it is great for what you're paying for, but almost guaranteed every single screw inside this machine is gonna have a random value of tightness, right? And none of the surfaces and the edges that look like they should be squared and parallel will be, at this level of precision. So basically, you need to, like, get an indicator, dial this thing in, and I'll show you some videos of that. And actually, there are right and wrong ways to turn a screw. This is actually really true. So What you need is like an infinite supply of like shim stock, right, and patience. And if you are doing this with a friend late at night, no one should talk because just like everybody knows like the right way to like shim a thing, but so lots and lots of patience, right, and shim stock. This took us like 2 days to really kind of dial the thing in, but you can do it. Once you do it, it'll stay more or less pretty close to perfect for what we need, and that's the mechanical chassis, right? So when we have that down, let's talk about how to move things, right? So like I said, for people who have like 3D printers, right? Everybody knows what this is. This is a stepper motor, right? Like it steps, it moves, and it's fairly, it's vastly mass manufactured, so very accurate for like an $8 thing. But then if you actually, so is this out of the box good enough for what we're doing? Probably not. And here's the thing, right? Like steppers, how do they move? People say, there's a step, you give it a pulse and it steps. But what is a step, right? Like something has to have a mechanical linkage that turns, takes that into linear motion. And a lot of things can go wrong if you have just this with a lead screw. So number one, you can have a bent lead screw, right? Lead screws can be imperfect. And number two, backlash, right? If you look at the threads of the nut and the lead screw, it's never 100% perfect, and it actually can't be. So there's going to be some back and forth give, right? So with that, and the stepper motor, how do you actually get precise movement for all sorts of industrial applications? And here's the right answer. Just you can convert money, right, into a really good hardware. And by that, we mean basically, like linear encoders and resolvers, which are analog, and you put this along the axis of movement, and this gives you an active feedback on where the motor, where the head of the thing actually is at any given time. So this is basically closed loop control, right? So you don't just tell it to move, you also watch exactly where it's going and how far it's deviated from its target. Okay, but that's kind of expensive. So there are there's a compromise, right? So on the left you have this thing called the Technic motor, right? It's made by a company called ClearPath. And basically what it is, it's a pretty good stepper motor, but it actually has a embedded processor, encoder, and lots of sensors inside, and a real-time management firmware that actually gives you closed-loop control just in a single package, right? You're not getting the linear encoder, but this will track very precisely rotational accuracy. But that's like $300 a pop, right? And then this beautiful thing on the right, it's $26, $27. And what it is, it's this is based on an open source project, right? It's a little PCB, so very much similar to this thing on the left, but instead of like a really nice optical encoder with high precision, right? This thing uses a Hall sensor, so you just super glue a magnet to the back of the rotary shaft, right? And there's a Hall sensor underneath this PCB that actually tracks, right, where it's going. So this is like a really elegant way of converting, like not great hardware into fairly precise closed loop control linear motion on an X and Y axis. And so we actually have videos on both of these. So I'm going to show you the one on the left. This is the Technic motor that we're using on the robot outside. And this is an indicator, right? So each tick here is 12.7-ish microns, right? So we're talking fairly small. It's not tiny, but, and we're going to basically move the thing back and forth to see how predictable, how reliable, and how precise and accurate motion control is, with just closed loop control on the rotational motor itself. Let's play. You'll never guess what happens. All right, so it's moving, right, and it touches, it settles there. I'm going to back off. I'm going to do it again. Ta-da! It goes back to exactly the same place. So, like we have, like 12 micron sort of per tick, indicators. So as far as we can see, like this is pretty good. And, so this is, like $600 of motors. They're great, but this is the same. This is another XY stage that we put together literally like 3 days ago, running the $26 closed loop control motor, right? And let's see what happens here. and this is actually at 0, so it's moving back. And it goes to exactly the same place. So with both of these, you can get very, very precise movement on standard, CNC hardware and a pair of either, slightly fancy motors or like a pair of like $30 motors. They both work. So with that, all right, cool. So that's kind of how we solved the movement problem. The next thing we had to do was figure out, like, if we can move precisely, how are we going to get this memory chip on and off, the FPGA and the target device without destroying the device or the memory? And the really cool answer here is this thing called silver ball matrix elastomer socket, right? It's super fancy, but this is, we have a few outside you can touch and play with and look at under a microscope. But basically, this is, I think they 3D printed, I'm not actually sure, but it is silicone substrate with columns of, I think probably also silicone substrate with doped small particles of silver or gold or something superconductive. And this is, like a side view. This is the top view, right? So this also has the consistency of like, I don't know, hard gummy bear, basically. So it's really good for compression socket, right? Like perfect for what we need to do. And the specs on these things are kind of ridiculous. So this is gonna do like, 40 gigahertz bandwidth for testing, like per pin. I think it can dissipate like, or push through like 10 or maybe a lot of power per pin. And also this thing works at minus 55C, which is special because that's basically dry ice territory and also the territory of where we need to cool our chip. So, but all of this, right? I don't know if you have bought stuff from Ironwood and companies like that. They're really great. They're expensive. But here's the next thing that was kind of a game changer. Okay, so this is Taobao, and we were able to buy this many elastomer sockets, 40, for this many monies. Right, so there are a whole lot of Chinese manufacturers now that actually will do custom runs of these. I think they 3D printed, and this is literally just like glued onto this little metal thing, right, for support. But it's very affordable now, and like I said, you can actually do super small custom runs of whatever footprint you want. And yeah, they're like, this much, like $30 a socket, which is great. And also, these sockets last forever, right? So they have like a test cycle rated for, well, okay, the Ironwood one has a test cycle rated for like tens to like 100,000 compression cycles. I don't think this one has it, but who cares, right? Like this is, I've never actually had a socket fail on us because of wear and tear. So these are really good and very much affordable. Okay, so that's number 2 down, right? And then number 3, let's talk about active cooling. So we started out with using dry ice, and instead of active cooling, we literally just had a dry ice isopropyl alcohol bath, right, in this little box where we dunk the memory chip and we cool it down before we actually run just the cold boot process, and that sort of worked. But also in the middle of last summer when we were doing this, the United States had a dry ice shortage, and I started thinking, that kind of sucks, right? And we also can't really store dry ice. It kind of evaporates over a few days. So we went to, started thinking of liquid nitrogen. And I said, you know what? Like, if there's one group of people who figured out like active liquid nitrogen cooling for like computer stuff, right? It's like PC overclocking people. And so I did some research, and it was amazing. So this is what they do, right? Like, this is the high-tech standard. So you take a thermos, you pour the liquid nitrogen into a bucket on top of the processor, and then you also take a torch to warm the bottom of it because of condensation and stuff. And this is the state of the art of like active liquid nitrogen cooling. I mean, I think Coolants sells this thing. It's like, I don't actually know how much it is, but it looks fancy and high tech, and I couldn't really understand like how to use this until I saw the video, and it's literally just you pour the liquid nitrogen by hand on a thing, right? I didn't like that. Like that's not really great. So here's what we did, right? We built this closed loop little. Basically, this is kind of like your typical like water cooling block for CPU or GPU. We machined it. This is every time I look at it, it looks like a little piggy with like in a blanket or something. But we machined this. And inside, right, we're pushing through isopropyl alcohol inside the tube, just like water cooling. But we're freezing this in below zero, so you shouldn't use water, right? It will freeze. So we ended up using isopropyl alcohol, and we have a pump here that moves the liquid through a heat exchanger that has another IPA bath. And what we do is we just cool the IPA bath, right? Liquid moves around, heat exchanger, right? Cools the head, right? And this is it's got the benefit that this can basically, you can cool the IPA however you want. You can throw literally just dry ice into the IPA bath. You can shoot liquid nitrogen into the bath. However you do it, it basically works, except so the vapor point for LN2 liquid nitrogen is like minus 195 Celsius, and the freezing point isopropyl alcohol is like minus 95 degrees Celsius, right? So you're not really going to have a problem with CO2, but if you use LN2, you're going to basically have to figure out a way how not to have the liquid inside freeze and block the path of the liquid. So we machined this in our shop, and the next thing we did is I tried a bunch of pumps. So I thought, hey, let's just get a pump and connect it. Like I had a few impeller pumps, but I found out very quickly that impeller pumps makes heat, right? And actually, the more powerful the pump, the more heat it makes. Makes a lot of sense because the impeller is literally coming in contact with the liquid you're trying to cool with the motor coil and all, right? So what we ended up doing is getting a parasolic pump, right? This is the sort of thing that you find in dialysis machines and things like that. It doesn't have nearly the same static pressure that it generates, but what is cool about this is it's literally like a set of rollers that pushes liquid through a tube, right? So the liquid you're trying to cool, in this case, never makes mechanical contact with the rest of the pump, so it doesn't introduce nearly as much heat. And I bought the biggest parasolic pump on McMaster, and that wasn't cheap, but it's a cool thing to have. So that pump is that works, and here is a video of basically the active cooling thing doing its thing. All right, so the cooler is literally outside, right? The IPA bath, heat exchanger, and in this case, we're just shooting liquid nitrogen into the IPA bath. And if you're doing this, like I said, making sure that the IPA doesn't freeze is super duper important. And the way to do that is essentially don't put the liquid nitrogen on top of the heat exchanger, right? Because it will go down to minus 195 and then come back up again. So you want to slowly lower the temperature of the IPA bath away from the heat exchanger. And if you do that, and also just put a heat sensor, a temperature sensor on the head, right? You can actually just put it into a pit loop and slowly decrease the temperature of the IPA bath, and that actually works pretty okay-ish, right? Sometimes you are going to get things that freeze, but if that happens, you just warm it up a little bit and start over again. Okay, so that's active cooling. All right, we got that down. Now, memory extraction timing, right? So if you think about it, we have to pull 5 chips. We can do this one at a time. We have these sockets, and what we actually did is, we took one memory module off, put the socket on, and then when we're done with that, we would solder the memory back on and do it to the next one and the next one. But if we had a 100 nanosecond window to do this reliably every time, right? This CNC is not going to be able to do that. Not really, right? That's kind of a hard target to hit. So does anybody have an idea how to do it? I mean, I'm presenting, so I should tell you. But think about it, right? So here was the little aha thing that we had. So we started measuring the EM, electromagnetic emanation, coming off of the device during boot. And what we were looking for is just periods of CPU-bound execution, right? Think back to Architecture 101, right? You have IO-bound, CPU-bound. And if you have CPU-bound operation, guess what it's not doing, right? It's not writing to memory. So instead of scale of nanoseconds, we have windows of tens of milliseconds where we can actually do the extraction. And this got around basically the requirement for super duper fast timing, precise timing extraction thing. So we found a bunch of these just by putting a near field probe onto a spectrum analyzer and then running the boot process and analyzing that data, right? So what does CPU-bound execution look like, on this thing? Well, you're not going to hear anything much from memory, and you're going to hear stuff on the CPU, right? So that's literally what that is. And yeah, we were able to find super wide windows where we can actually do this timing, and that was the thing that allowed us to reliably extract memory and then stitch it back together across 5 chips. We did like tens of runs, and it worked. Okay, so that's 4. That's 4 down. Next thing is how do we do the actual DDR memory dumping? So we started with LPDDR1, and for that we actually designed our own PCB carrier board that goes onto a zinc FPGA and the whole thing, right? This took a lot of time to do, and if you guys have tried to actually like design a PCB with DDR memory, right, like impedance matching, all that stuff was, you have to get that right, and it was kind of a nightmare. But then we started thinking about like DDR2 and 3, and it turns out you can just buy dev boards, right, with FPGAs on it with that memory footprint, right, already there. So Digilent did all the hard work for us, and we literally just put a socket on this thing. It took like no time at all, and it worked much better. And this is DDR, so this is 1, DDR2, and DDR3 is even better, right? So, like this is even cheaper of a FPGA board. And yeah, like right now, if you want to do DDR4, you're gonna pay some, like money for like a FPGA with that memory socket, but it's very doable, right? And then we just wrote this, it took like 2 minutes. FPGA is easy, right? Like we didn't have to debug at all. Like that's it, right? So I mean, this wasn't terribly complicated. Well, I shouldn't say that. I didn't do this. Someone else did. But yeah, basically this is a DDR3 memory controller hooked up to the AXI bus, right, running on the Zinc board with the memory interface thing, right? So that's what we did. And then after that, right, so let's review. We built, did we do a sufficient precise linear motion thing? Yes, we did, right? Could we actually find a cool socket? Yep, they're $30 a pop, elastomer. And then can we do closed loop control, like a closed loop cooling on the RAM chip? Sort of, basically, right? And then memory extraction timing, right? CPU bound operation, like totally works. And then DDR1, 2, 3 RAM dumper, right? Like, FPGA, right? We did get that to work. So with all of that done, this is what it looks like. And this is actually a video from last year. And if you notice, right, this thing didn't have an active cooling system. This was just a Cisco phone on the DDR3 FPGA board. But let's see it work. All right, so there's like a little bath area for cooled isopropyl alcohol, right, where the dry ice doesn't touch. So we're cooling the memory. We dab it on some paper towel for condensation and things. We put it on the Cisco phone. We see it booting up, right? And at the right time, we literally take the memory chip off and we put it on our FPGA, and then we get to read it. Like, boop. And it works. Yay, And then later on, we added something like I got a case for it, and now it has, like a fairly cool control system. And these are the pneumatic valves that we have, right? Power supplies and all this stuff, temperature sensor, PID loop for real-time control for the temperature and liquid nitrogen valve thing. And yeah, so this is the state of the robot today, and it is fairly reliable and repeatable. So, one cool thing about doing it this way versus like an interposer, right? You can basically arrange, the PCB, whatever you're working on this grid, and just dial it in with an indicator. It's super duper flexible. All right, so with that, then let's see. Okay, well, all right, these are the videos. Oh, right, and then there's a happy ending to like the Epic Win thing, right? On the S717 or 1500, what we found is that all of those devices just did symmetric decryption for bootloader verification instead of signature. Yeah, like that's how all of those things run, and they're using this this ATEC chip to do that encryption. And what we did is, we looked at the bootloader, saw this thing, found the chip, and just took that chip off, used it as an oracle to basically encrypt bootable images for all of the S7s in the world. So, without the Copu robot, we would not have actually gotten to see the code to a point where we actually can read how it's booting up to find this vulnerability. So yeah, like Kobo Robot after 7 months of failure totally worked out. Yeah, I think that's it. It's outside. You should play with it. And yeah, so I think questions, comments, feelings. Oh, yay. Yes. Yeah. Oh, okay. This is really good. So the question is, can we pull the memory chip off at multiple times of execution? So the naive, straightforward way is no, because as soon as you pull the memory chip off, the device generally crashes because it doesn't love having its memory just ripped out. But this is we have a few really interesting sort of open questions that we're experimenting with. So with the active cooling, right? Is it possible to put the memory chip back on the device or a different memory chip, right? Because if you can do that, you can actually kind of just DJ like physical memory, right? And have it execute and pause and execute and pause. And I don't know, so we're playing with that. But if you look at the DDR state machine, so with DDR memory, right, it's not as simple as just read thing from parallel interface. It actually has a pretty complicated state machine of pre-charging, charging, like writing, idle. But that said, though, right, you can probably, if you know the state of the memory controller in your device, yeah, you can probably predict that, and then with your FPGA, put the physical memory chip back onto that state. We don't know yet, so that is definitely like a thing that we're experimenting with now that we have active cooling on this thing. And then a second point that we're looking at, and this is kind of a cool thing to think about, right? So we know that memory has maximum frequency that it can operate at because, like computers, heat, all that stuff. But does it have a minimum frequency, right? And the answer is like, yes, like that's not the profound part. Like it does have a minimum, but what is that minimum? And can we extend that lower, right? If we cool the thing super duper great, because, if we can do that, we can use slower hardware to do the reading, right? Instead of like a 2 gigahertz memory interface on an FPGA, which is like very expensive and not doable. If we can push that down to like, I don't know, like single megahertz, right? We can, like a lot more hardware is in play for building the memory dumper. So, good question. Anyone else? Yeah, this won't work for encrypted memory, right? I mean, it might if you can somehow get the key, right, for the ephemeral memory. But yeah, like this is basically, well, I mean, that's probably much more complicated. But yeah, the short answer is if you have ephemeral key negotiation and memory encryption on the hardware, right, you're going to pull out encrypted memory, which you probably won't be able to decrypt. So it won't work. Oh,
Hi. Can you comment on the process of rebuilding, going from these 5 images, from these 5 modules, to rebuilding the actual RAM?
Okay, all right, cool. So yeah, I have a few minutes. Okay. So for the details on that, read the paper. But so yes, we pulled the 5 memory chips off. We were pretty sure we had the right timing, and then we tried to put the thing together, and we tried every permutation, right? Knowing that there's probably ECC, and none of them worked, right? Like was not any, like it didn't decode to any code ISA that we can decode, and no strings of any kind, because the actual bits are shuffled, right, across all of the 5 memory chips, and not just like one byte after another byte after another byte, because it's not a security feature. It was just, I think, easy for routing on the PCB. But then we did entropy analysis on the bits we got, and it is code and data, so low entropy sort of content. And then we did like 2 weeks of things trying blah, blah, blah. And then eventually, we had this insight that, maybe there's probably a AES constant somewhere in this memory, right? And we actually did some statistical analysis to figure out like what the most likely permutation of the bits are. And like long story short, we actually got that to work, and we were able to get the actual bit ordering across the 5 chips and figure out the ECC algorithm, right, on the fifth chip. But statistical analysis and a lot of like trying things out. Yeah, no, it's the same chip. It's the same chip. Same key, right? Yeah, that's not the right way to do it, and that's what we found. So yeah, the idea is, in reality, you can buy any S7 1500, right? Take the ATEX chip out and use that to encrypt more memory, and if it decrypts, it boots, right? So that's not a signature verification, and that's part of the problem, right?
How did you actually remove the chip without damaging it if you're having to keep it cold at the same time?
Well, so removing the physical chip wasn't terribly difficult. We just hot air reflow, right? Took that off, cleaned the bottom, reballed it. And actually last year we ran a reballing workshop for that reason. And then the chip is actually just super glued on top onto the piston brass block. And there are definitely tricks to lining that up right. So if you're interested, we can show you outside with the actual robot. Over there? Yep. Yeah. Yeah, I mean, we'll do that on Sunday maybe, like, yeah, we can do that on Sunday. It'll break. Ooh, and also, it just so happens, I always get this wrong, the Xbox S uses the exact same memory footprint as the Cisco phone, and I have 2 Xboxes with the sockets on it. So if we have some time, we should try to pull the memory off on the bootloader. Yeah. But for that, there's 16 memory modules, so patience. All right. Anything else? Okay, all right, I think that's it. Cool, thanks.